Okay, so right triangle trigonometry, we're going to identify the 6 trig ratios starting today. And first, I want to just talk about trig ratios in general. Okay, when I talk about a trig ratio, it means I'm creating a ratio with 2 side lengths in a right triangle. So we know, and a lot of people probably put on their papers, triangles have 3 sides. When we create these trig ratios, we're not using all 3 at once, we use only 2 of the 3. Often in our notes, I'll use the triangle symbol to write the word triangle because, of course, I'm lazy. I don't want to write it all out. What do ratios look like? When you see a ratio, what does it look like to you? Okay, one way is, the old way is to have the colon and then there's 2 numbers on either side of the number, and Eric does a great job. He says the colon and then you're comparing the 2 numbers, like a 2 to 3 ratio with a colon in the middle. And then Sierra, you said it also sometimes looks like a fraction where you have like a 2 to 3 ratio where 2 is in the numerator and 3 is in the denominator. We are going to be seeing our trig ratios as fractions. So like on your homework tonight, all your answers for your trig ratios should be fraction form. Okay. I have a right triangle drawn here. And then in one of the acute angles, one of the angles that are less than 90 degrees, I have the angle labeled with a Greek letter, and that letter is theta. Okay, so I'll write on the board, and you might want to write this like in the margins of your paper. When I'm just writing theta out, I normally write it almost like a capital cursive O. It's like an O with a little curl at the top. To me, that's fine for theta. Some of you will draw your theta so it looks more like the typed version of theta, where you put a line in the middle of it. Either one of those is acceptable. Okay? But both of those are read as theta. And it's common in the study of trigonometry to use theta to represent angle measure. So in chapter 9, anytime we come across a theta, the theta means angle measure. So you're talking about an angle. Now, does anybody remember what the 3 trig ratios are, bless you, that you already know? Faith? Sine, cosine, and tangent. Excellent. Remember that when writing out the trig ratios, sine, cosine, tangent, there's always something that comes behind them. In some cases, like in geometry, you might have just used capital letters like A, B, C. And then in algebra, we're going to switch it over and use the theta. And then sometimes, like tomorrow when we practice with our calculators, if you know that you're looking for the sine of 50 degrees, you might have an actual angle measure in degrees back there. Okay. But you can never just have SIN equals. There has to be something after it. And then is anything else coming to mind about sine, cosine, and tangent? Justin? Oh, there are some other ones, and they're not the ones that are the other 3 trig ratios that we're going to talk about, but you are thinking, he says, with the -1. Like this? Yeah. Okay. These are inverse trig ratios, and they're actually going backwards. Instead of putting in an angle and getting out a ratio, like putting in the theta, you're actually putting in a ratio behind the sine, the cosine, and the tangent, and then your answer is the angle. Okay. So we will study the inverse trig ratios, but it will be later on in our chapter. Okay. Anything else you remember, Bailey?
You know, like the SOH, CAH, and TOA?
Yes. What did you call that? SOHCAHTOA, right? SOHCAHTOA. Excellent. Let's write that down. I would definitely recommend writing SOHCAHTOA in your notes. Now, how do you use SOHCAHTOA? What is helpful about it?
Helps you remember what's over what.
Oh, it helps you remember what is over what. So Faith, you're going to add to that and say?
Yeah, it's like for sine, it's opposite over hypotenuse.
Sine is opposite over hypotenuse. Cosine is?
Adjacent over hypotenuse.
Adjacent over hypotenuse. And tangent is opposite over. Oh gosh, I'm having a hard time writing. Adjacent. Ring a bell? So how do those words that you're using there, opposite, hypotenuse, adjacent, translate up to that right triangle picture that we have? Where we have our theta, we should label all three sides of this triangle in relation to this angle theta. Okay. So it's always easy to identify which one is the hypotenuse because it's across from the right angle. And I saw some people writing on their sheets, the hypotenuse is always the longest side. Some people said that. And then for opposite and adjacent, which one's opposite, which one's next to theta? Okay. The side that with the hypotenuse makes the angle is adjacent. And then here we have our opposite side. Maybe write out the full words for you. Good. So we're going to be doing a lot of SOHCAHTOA this chapter. If you liked SOHCAHTOA in geometry, it's a good thing. If it wasn't your favorite, you're stuck. But chapter 10 will be totally different. Now, there's 3 more trig ratios that we haven't gotten to yet. And Justin brought up the 3 that have been brought up in most of the other classes as well. They're the inverse trig ratios. But they're actually still not working with the angle. They're going backwards. So the other 3 trig ratios, I'm going to show you what their abbreviations are written as CSC, SEC, and COT. CSC, SEC, COT. And these are just abbreviations. How do you say them? I'll write them over here on the side. The first one is cosecant. Cosecant. Brand new term. Just like when the first time you learned sine, the first time you learned cosine, the first time you learned tangent. What the heck? Okay, new term. SEC is called secant. Think about how those two are related to like the names that we already know. Sine, cosine. We have a secant and a cosecant. And the last one is cotangent. So that one's not so weird. Now, the interesting thing about these 3 new trig ratios is instead of being called inverse trig ratios, which is what Justin gave us, that -1, these 3 are called reciprocal trig ratios. And what does the word reciprocal mean?
Opposite.
What do you mean opposite?
Like
Flip.
flipped around.
Oh, flipped. So when we're talking about a fraction, we're going to move the numerator and the denominator and switch places. So that's all you have to do for those three. If you already know how to do sine, cosine, and tangent, to do the other three, you only have to flip them. So these three, the reciprocal of sine is cosecant. That's why I have them on the same line there. So I'm just going to flip opposite over hypotenuse. And cosecant is hypotenuse over opposite. Cosine has a reciprocal that is secant. So I flip adjacent over hypotenuse, and it's now hypotenuse over adjacent. And cotangent is the reciprocal of tangent, so it's adjacent over opposite. My one warning about these reciprocals are a lot of times it will be common when we're first learning to want to group like the C's and the S's together. So you might want to say sine's reciprocal is secant and cosine's reciprocal is cosecant. But it's actually switched. So I always just remember that the C's and the S's mismatch. The reciprocal to sine is cosecant. The reciprocal to cosine is secant. Okay, so they mismatch. Does anybody have any questions about this slide before we move on and look at an example? Okay, we're going to draw a picture in our notebook. For example 1 should be a right triangle. Make sure that you draw the right angle. Then make sure you label 3 things. The theta. Oh, theta did not appear right now. Don't know why. That little rectangle is supposed to be theta. Draw the theta and then label the 2 sides. Here's the theta. Sorry about that. Our goal for today, and what you'll be doing on your homework, is to be able to find all 6 trig ratios. The 3 that you know from geometry, and then their reciprocal ratios, where you just flip them. So I usually just start by thinking about my triangle. Can I do sine, cosine, tangent? What do you think about the triangle that you're provided, and then being asked to find all 3 trig ratios? Are you ready to find all 3? No, what are you missing? The what?
Third side.
The third side. Can you find the third side in a right triangle? Using what? The Pythagorean theorem. Remember your good old friend from geometry? A squared plus b squared equals c squared. So we're going to do a squared plus b squared equals c squared. And remember that when you're plugging into Pythagorean theorem, c always needs to be the hypotenuse. So if we think about that here, we know this side is our hypotenuse, so we're going to leave that as a variable. This side is our opposite, and this side is our adjacent side. So those are going to be our A and B, but it doesn't matter which order we put them, because they get added together, so it doesn't really matter. So I'd say something like 3 squared plus 4 squared equals c squared. And that's 9 plus 16, or 25. So what's that missing side? 5. Good. So you guys are very well skilled at finding the missing side with Pythagorean theorem. Now can you find sine, cosine, and tangent? Sure. Okay. Using SOHCAHTOA, that great tool. So is opposite over hypotenuse, so 4 over 5. Ka is adjacent over hypotenuse, so 3 over 5. And tangent would be opposite over adjacent, so 4 over 3. And then the only thing I'm asking you to do in addition to that is now write out those three reciprocals. So you would add to this cosecant, secant, cotangent. And I'll tell you, I don't even really look at the triangle. I just look at the three ratios I've already written down and I flip them. So that will give me 5/4, 5/3, 3/4. I'm done. Our trig ratios look like fractions. Okay, I don't need you to type them into a calculator and get a decimal. We can leave them as they are. Do you remember 3, 4, 5 is called a Pythagorean triple? Do you remember any other Pythagorean triples besides 3, 4, 5? A Pythagorean triple are three integer numbers, so like whole numbers, that work in the Pythagorean theorem. So like 3 squared plus 4 squared equals 5 squared. Another one that maybe what you would recall from geometry was like 5 squared plus 12 squared equals 13 squared. So 5, 12, 13 is a Pythagorean triple. That was a common one that you probably saw a lot. And also there's like, you can take 3, 4, 5 and you can multiply all the numbers by the same factor. So like multiply them all by 2, 6, 8, 10 also works in the Pythagorean theorem. Those are just helpful things that might like reduce the amount of work you're doing. Okay. I'm going to give you a second example. I'm going to give you some time to work. I want you to use the aid of your shoulder buddy or small group people around you to complete this. It's the same setup in that I want you to find the missing information that you need. I'll put my theta up there momentarily. And I want you to find the 6 trig ratios. I will tell you something about this problem is different than the problem we just did. Okay? And once you get started, I think you'll find out what is different from the previous problem. So I'll give you some time to work. Use your shoulder buddy. Compare the missing side to make sure that you're getting the correct missing side. And then we'll talk about this in just a moment. Probably all doing things correctly. But we solved for the missing side, which turned out to be a radical. And again, I don't want decimals here. I want you to leave things in radical form. If you can do the factor tree, do the factor tree to make it smaller. Okay? But otherwise, leave it alone. And then she just goes about her merry way, doing SOHCAHTOA, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, to get sine, cosine, and tangent. And then she flips them to get cosecant, secant, and cotangent. Are there any issues as you look over Sierra's work that you think should be addressed?
I thought radicals aren't supposed to be, well, these aren't fractions, are they?
They're fractions.
Okay, so it's not supposed to be in the,
Oh, how nice of Sierra to critique her own work for you so you didn't have to do it. Good. She says she thought radicals weren't supposed to be in the bottom of a fraction. Do you remember hearing that? That's true. So if you gave me that answer on a quiz or a test, I'd take off minus 0.5. Because there are 2 trig ratios that need to be fixed. They are cosecant and cotangent. To rationalize the denominator or get rid of the radical in the denominator, just multiply by whatever radical is down there. So I'm going to multiply by the square root of 33 on the bottom, and then I'm going to multiply the top by the square root of 33 as well. So that gives me a final answer here of 7 square root 33 over 33. No more radical. To us, it doesn't look a whole lot better, but that's the way we want to see it written. And we would do the same thing for cotangent. Multiply by the square root of 33 on the top and the bottom, and you're going to come up with 4 square root 33 over 33. Now you should always check like the numbers on the outside, 7 over 33, 4 over 33, do they reduce? Not in this case. So we're good to leave it alone. Are there any other issues you want to talk about?
Why do we not use decimals for this one?
It's only because it's, when you use a decimal, you are then rounding. And then if you round before you divide, then your new divided answer is also rounded. So the goal here is that we get exact values, and that just means we leave it in radical form. There's one other small, tiny point about what Sierra wrote on the board that I wouldn't take off for this, but we'll be nitpicky when we talk about it. What's missing in her trig ratios? The theta. Yeah. If we were going to be really nitpicky, you can never have sine equals. It has to be sine of something equals. So we should go back and we should throw that theta in after all our trig ratios. Jackson.
So, the theta is a number.
Theta, yes, there is an angle. There is a value for the angle where its sine will be square root 33 over 7. There's one angle that does that in a triangle. And so, yeah, there's a number. We don't know what that number is. Is that a 47-degree angle or a 32-degree angle? We don't know. We're just comparing the side lengths. Okay. Your homework assignment for tomorrow is page 466, numbers 5 through 8, 13 through 16, and 19 through